Hello everyone, this is going to be a quick video on how to draw Lewis structures. Lewis structures are an essential part of chemistry and they never really go away. Learning how to do one correctly will save you a lot of time and will help improve your grade. Now the first thing we do when we're drawing a Lewis structure, such as one for carbon dioxide, CO2, is we're going to count the valence electrons. This lets us know how many electrons we have to work with. Let's start with carbon. Carbon has a valence of 4, and you can find that out by counting across the group numbers. So carbon is in group 1, 2, 3, 4. It's in group 4A, so it's going to have 4 valence electrons. Now try finding the valence electrons for oxygen in the same way. For oxygen, you're going to count across 1, 2, 3, 4, 5, 6. And we have 2 oxygens, so we're going to multiply that by 2. And you may have noticed we kind of skipped over these guys. These are the transition metals, and we cannot count valence for them in this way. They're kind of an odd guy, or odd guys, so we're just going to ignore those for now. Now if we go down here, 4 plus 2 times 6, that's the same as 4 plus 12. And that will give you 16. We have 16 electrons to work with. Now let's start by drawing a basic structure. Carbon is going to go in the middle because it's the least electronegative. You never put the most electronegative thing in the middle, it's always going to be least. An exception for this is hydrogen. Hydrogen can never have more than one bond. So if you see something like this, that is wrong and you're going to have a bad time. Never more than one bond for hydrogen. Back to carbon, we're going to have a carbon on one in the middle, and have oxygen on either side. Now each single covalent bond represents 2 electrons. And if we count here, 2, 4, we've used up 4 electrons. 16 minus 4 is 12, and we have 12 left to work with. Another thing about carbon is that it always has 4 bonds. It will never ever have 5. If your carbon has 5 bonds, you might want to reconsider your structure. On the odd occasion, it will have less than 4 bonds, but those are not seen very often. So to make it 4, we're going to put another 2 bonds on carbon. We've used up another 2 4 electrons, and 12 minus 4 is 8. We have 8 electrons left to work with. If you look at carbon, it has a full octet. It has 2, 4, 6, 8 electrons around it. There's nowhere else we can put it on carbon. So let's start sticking them on oxygen. They already have 2, 4 electrons next to it. So we're going to add another 4 to make it 8. 2, 4, 6, 8. We're going to do that on the other side. We've used up 1, 2, 3, 4, 5, 6, 7, 8 electrons. 8 minus 8 is 0. We don't have any electrons left over. Now let's do our formal charges. Oxygen has a valence of 6. We're going to subtract the number of electrons on it, which is 1, 2, 3, 4, and count the number of bonds, 1, 2. 6 minus 4 minus 2 is 0. That is a good, stable, happy oxygen. Let's do the same for carbon. It has a valence of 4 minus 4 bonds minus 0 electrons equals 0. And you might be able to eyeball the oxygens and see that they look the same, and it will have the same formal charge, but let's write it out. It has a valence of 6 minus 4 electrons minus 2 bonds equals 0. We have the lowest possible formal charges, which is a 0 on everything, so this is a good, stable structure. And the reason we count our valence electrons is we don't have an unlimited amount to work with, and in this we did, but we don't. So you need to figure out how much you have before you can start building your structure. Now I encourage you to sit down and try doing SO4 2- before I walk through this. So pause the video and give it a go. Okay, hopefully you paused the video, give it a go. And now I'm going to walk you through it. The valence for sulfur is going to be 6. We count over 1, 2, 3, 4, 5, 6. So we have 6 electrons for sulfur. And we're going to do the same for oxygen. 1, 2, 3, 4, 5, 6. And we have 4 oxygens, so that's going to be 4 times 6. Now a big difference from what we did before is we have this -2 charge here. When you have a negative charge, that means you're going to add electrons to your total valence count. So we're going to have to add 2 more. If this had been a positive charge, we would have subtracted electrons from our total count. Now 6 plus 4 times 6 plus 2 equals 32. We have 32 electrons to work with. Now look at the molecule and ask what is the least electronegative thing in there. And if you're having trouble with it, write out Funkelbrice. F-O-N-C-L-B-R-I-S. And this is a list of your most electronegative elements. Now, oxygen comes before sulfur, goes from most to least, most electronegative, to least of the most electronegative. Oxygen comes first, so it's going to be more electronegative, so that is not going to go in the center. Sulfur, which is the least electronegative here, will go in the center. Now, a quick side note, things that are in period 3, or if you're not familiar with the term, row 3, things over here and down can have an expanded octet, which means they can have more than 8 electrons around them. So sulfur is going to go in the middle, and you have no other choice but to put 4 oxygens around it. Now in doing so, we've used up 2, 4, 6, 8 electrons. And 32 minus 8 is going to be 24. We have 24 electrons to work with, and get rid of that little 8 from the last problem. Now here we have a charge of -2. So that means somewhere in here, when we do our formal charges, we're going to have at least one thing that has a -2 charge, or 2 things that have a -1 charge. In problems like this, the charge is going to go on the most electronegative atom, or atoms, because they want the electrons the most. So in this case, this is going to be oxygen, since it's going to be more electronegative. And the thing about having an oxygen with a charge is it follows a pattern. If you have a -1 charge and you know it's going to be an oxygen, it has to fit this pattern. It's the only way to get a -1. And you can use this little shortcut to make drawing your structures easier. This has 1, 2, 3, 4, 5, 6 electrons on it. So let's add that here. 1, 2, 3, 4, 5, 6. And we have a -2 charge, so we're going to have to do that one more time. 1, 2, 3, 4, 5, 6. We've used up 2, 4, 6, 8, 10, 12 electrons. So 24 minus 12 is going to be 12. And the more you do these, the more you start to recognize these bonding patterns, and it will make things easier. These should not have any charges. We already have a nice -1 charge here, and you check that by doing your formal charge. 6 valence from oxygen, minus 1, 2, 3, 4, 5, 6 electrons, minus 1 covalent bond, gives you a formal charge of -1. So you know that this is going to work out. To get kind of a neutral atom in the structure, you're going to have to have double bonds between the oxygens and the sulfur. And we used up another 4 electrons. 2, 4. 12 minus 4 is 8. Now you may look at this and think, this can't be right. Sulfur has more than 8 electrons around it. But sulfur is in group 3, and those can have an expanded octet. And sulfur is kind of notorious for violating the octet rule. So you're fine, don't worry about it. So you're going to have 2, 4, 6, 8, 10, 12 electrons around sulfur, and it's going to be fine with that. We can have expanded octet. Now we have 8 electrons left, and we need to put those on oxygen. But start putting electrons on the things that you know are going to be more electronegative. So you can put 1, 2, 3, 4 electrons here, and 1, 2, 3, 4. We've used up 1, 2, 3, 4, 5, 6, 7, 8 electrons. 8 minus 8 is 0. We don't have any more electrons to work with. Now to see if we did this right, we need to check our formal charge. Sulfur, probably done a different color. Sulfur has a valence of 6. We count the number of bonds around it. 1, 2, 3, 4, 5, 6 has 6 bonds, minus 0 electrons. 6 minus 6 is 0, and sulfur is happy with its formal charge. When possible, try to get a formal charge of 0. Now let's count it for this oxygen. Oxygen has a valence of 6, minus 4 electrons, 1, 2, 3, 4, minus 2 bonds, 1, 2. 6 minus 4 minus 2 equals 0, and this guy is going to have the exact same formal charge. Now these guys have a different bonding pattern. They only have one single bond. Let's check the formal charge. Oxygen has a valence of 6, minus 1, 2, 3, 4, 5, 6 electrons, minus 1 bond. That gives you negative 1. And this guy over here is going to do the exact same thing. 6 minus 1 gives you negative 1. Now, when you add your formal charges together, you should get the same charge as the thing you were originally trying to draw. So negative 1 plus negative 1 gives you negative 2. And that matches what we were originally trying to do. This is a good, stable Lewis structure. Now I encourage you to pause the video and try it for H2SO4. Or try it while I'm erasing the video. Or erasing the writing. Now hopefully you've tried it, and you've hopefully counted your formal charges. If not, pause the video and go do that. First thing we're going to do is, if you guessed counter valence, you are right. Hydrogen has a valence of 1. It's over here in the first root, so 1, and we have 2 hydrogens. It's going to be 2 times 1 plus the valence for sulfur, which is 1, 2, 3, 4, 5, 6, plus the valence for oxygen, which is 1, 2, 3, 4, 5, 6. And we're going to multiply that by 4. You're going to add these together. That is going to be 4 times 6, or if you want to count the 6 here, 5 times 6, which is 30, plus 2 gives you 32 electrons to work with. Now take a second and look at what may go in the middle. Oxygen is more electronegative than sulfur, so that's not going to go in the middle. Hydrogen can never have more than a single bond, so it can't go in the middle. The only thing we have is sulfur. Sulfur goes in the middle, and you're going to start by putting the oxygens around it. You're going to have 1, 2, 3, 4. Now, a quick note is when you see structures or formulas like this written out, these hydrogens are probably going to go on the oxygens. Might be tempting to just stick them on sulfur and call them a day, but unfortunately it does not work that way. So you know you're going to have one hydrogen on an oxygen and another hydrogen on the oxygen. And let's count up how many electrons we've used up. So we've used up 2, 4, 6, 8, 10, 12 electrons just by making the basic structure. So 32 minus 12 is 20. We have 20 left to work with. Now we're going to start by filling up the octets around oxygen. This has 2 4 electrons, so we can add another 2 to get 6, and another 2 to get 8. Repeat that on the same side. We've used up 8 electrons, so we're going to subtract that from our current total, leaving us 12 left to work with. Now looking back here, we see that H2SO4 does not have a charge on it. So the oxygens probably are not going to have a charge. And to prevent these from having a formal charge of -1, you need to double bond them to sulfur. We're going to add another bond. So we used up 2 4 electrons. 12 minus 4 is 8. Sulfur has 2, 4, 6, 8, 10, 12 electrons on it. It's going to be fine. But these still have an unfilled octet. So we're going to start adding electrons. We're going to add 1, 2, 3, 4. So we have a total of 2, 4, 6, 8. We're going to do the same on the last one. We've used up 8 electrons. 8 minus 8 is 0. We have no more electrons to work with. So now you're going to check your formal charge. Starting with hydrogen, 1 minus 1 bond minus 0 electrons equals 0. That's good. Oxygen has a valence of 6 minus 1, 2, 3, 4 electrons minus 1, 2 bonds. That gives you 0. And this guy is going to be the same. So you're going to now look at these oxygens, which I'll do in blue. These have a valence of 6 minus 4. Oh dear. I apologize. My pen seems to have malfunctioned. Be 6 minus 4 minus 2, 4 electrons, 2 bonds. That equals 0. Or this guy's going to equal 0. This hydrogen over here, 1 minus 1 valence minus 1 bond minus 0 electrons equals 0. This is a good structure so far, and let's do it once more for sulfur. Sulfur has a valence of 6 minus 1, 2, 3, 4, 5, 6 bonds minus 0 electrons around it, and that is going to equal 0. All of our formal charges are 0, which is what we wanted if we look back at the original structure. And this is stable. Good job, guys. Now, I encourage you to practice this more on your own. The more you do it, the easier it gets.